The energy system is transforming. To achieve carbon emission reduction targets, the world's electricity production is shifting away from traditional fossil fuels such as coal and natural gas to renewable sources such as wind and solar. Consumers are turning into so-called prosumers by installing solar panels on their houses and generating their own electricity. With regard to transportation, electric vehicles are steadily gaining market share, replacing regular combustion engine vehicles. My name is Amy and I'm a strategy consultant at Stedin Group, the third largest distribution network operator for electricity and gas in the Netherlands. At Stedin Group, we are continuously thinking about the energy system of the future. Energy system integration is increasingly believed to be the next step in designing future-ready energy systems. In this series of 3 videos, I will talk about important developments and considerations with regard to energy system integration and one of its key enablers, hydrogen. We will start off this series with an introduction to energy system integration. The EU Commission's Energy System Integration Strategy, as published in July 2020, defines energy system integration as the coordinated planning and operation of the energy system as a whole, across multiple energy carriers, infrastructures, and consumption sectors. However, energy system integration is a relatively new concept within the energy sector. As a result, there are still many different definitions for energy system integration floating around. In general, we can state, though, that energy system integration requires a holistic view of the energy system, whereby synergies between the different elements are mainly directed at increasing the share of renewable energy and reducing the system's CO2 footprint to make the system more sustainable. Second, strengthening system resilience. And third, lowering system costs to ensure affordability. Balancing these objectives is at the core of energy system integration. The following picture is a simplified representation of the energy system. Let's assume we have 4 different types of energy carrier networks: electricity, hydrogen, a methane-based gas, such as biogas, and heat. These networks can be used to transport energy from an energy source to energy demand for different sectors. To balance supply and demand in the system, storage is added for each of the energy networks. Traditionally, networks of the different energy carriers interacted minimally. Adding new technologies such as electrolyzers, which are able to convert electricity to hydrogen and back again, or heat pumps, which are able to provide heat to households by using electricity, allows for coupling of energy infrastructures. As the name indicates, system integration is about connecting the different elements of the energy system. As the energy system encompasses many layers, integration occurs on different levels. The first type we consider, as demonstrated by the different technologies in the previous slide, concerns the integration of energy carriers and infrastructures. Second is the integration of different production and end-use sectors, also referred to as sector coupling. Using batteries of electric vehicles as battery storage to relieve congestion integrates the electricity sector with the mobility sector, 2 sectors which were previously separated. Another example is the use of residual heat from industry to heat households nearby. There are many more examples of sector coupling opportunities. Third is the integration of smart infrastructure assets and connected agents. This concerns the most complex form of energy system integration, whereby the entire system interacts with other elements in the system. As a result, smart assets within the system should be able to interact autonomously with other assets, but also agents such as businesses and consumers, to optimize based on a system level rather than individually. This requires a completely digitized system. As I mentioned before, system integration is about creating synergies between the different elements to optimize the system for a certain goal. To make this a bit more concrete, I have defined 3 common objectives of energy system integration into use cases, which are: first, to accommodate the integration of variable renewable electricity generation and reduce the system's CO2 footprint. Second, optimize infrastructure investment and operation cost. And third, improve customer business cases. We will walk through examples of each of the optimization use cases. Renewable electricity sources such as wind turbines and solar panels are so-called variable electricity sources, of which production is dependent upon prevailing weather conditions. As a result, electricity supply has become less stable, making it more difficult to balance supply and demand, possibly resulting in power system outage. This graph depicts a possible average week in summer, whereby solar production causes large peaks that are much higher than electricity demand. Using energy system integration, excess production in summer could be converted into hydrogen through electrolyzer technology, also referred to as power to hydrogen, and stored for longer periods of time. In winter, when electricity demand is generally higher than supply, this hydrogen could be converted back to electricity to be used in, for example, electric heat pumps. As such, energy system integration allows for balancing energy supply and demand in the system. In addition to balancing problems, the electricity system is also experiencing capacity problems due to a number of reasons. One of the reasons is the decentralization of electricity production. Unlike traditional power plants, which due to their scale were established in centralized locations, small-scale wind projects or solar fields are emerging in various locations in the grid. Transporting electricity directly from these locations, as an option A, have resulted in operational and financial challenges for grid operators to expand or reinforce the entire existing electricity grid. As the frequency of these issues increases, the system may experience local congestion problems. Another option, option B, is to convert locally generated solar energy to hydrogen and distributing the energy through the gas grid rather than tapping into the electricity grid. This could postpone or even avoid infrastructure investment costs for grid operators. As such, energy system integration can help optimize utilization of existing infrastructure assets and reducing system cost. In the next video in this online course, we will discuss the role of hydrogen in energy system integration in more detail. This graph depicts the net energy load of a prosumer on a summer's day. Typically, solar panel production is highest during the afternoon, whereas energy demand is lowest during the day, causing a negative net load. The blue area under the graph represents the solar panel production fed back to the grid. This does not only cause capacity problems for grid operators, but also affects the household's business case, as they could have used this electricity later on. If a household in possession of solar panels and an electric vehicle were to charge its electric vehicle at time of peak solar panel production, it will be able to increase the consumption of its production. We will conclude with some key takeaways. Energy system integration comprises a holistic view of the energy system, whereby different energy carriers, infrastructure, and consumption sectors are regarded as a whole. Integration of these different elements aims to increase the level of sustainable energy technologies, strengthen system resilience whilst reducing system cost. Energy system integration is therefore used to optimize the system based on these objectives, and can be a driver for new business models. In the next video, we will take a closer look at the hydrogen economy and its potential to fuel the energy system of the future.